If you want to perform a spatial drawing on this one single dataset, if you don't have an efficient or scalable engine, it's just going to take you forever. It probably don't crash even. It just keep running, and you're going to spend your whole life on that.
We've all been there. You hit run on a query, walk away to get coffee, come back, and it's still running. Or worse, your machine has crashed. But what if you need to process not just gigabytes, but petabytes of complex spatial data? Today, I'm sitting down with the person who built the engine to solve exactly that.
We started the Sedona project a little bit over 10 years ago. Fast forward to now. So right now, the monthly downloads of Sedona is about like 2 million per month.
That is Jia Yu, the co-creator of Apache Sedona and co-founder of Whereabouts. In this episode, we go deep into the weeds of why geospatial data breaks traditional computing models.
It is about everything. So longitude, latitude, polygon boundaries, trajectories, right? Satellite images, drone images, LiDAR data. They're very different. It is so hard to process, right? So this kind of multimodality problem make really hard to process all the geospatial data in one place.
We trace the 10-year journey from an academic project to a top-level Apache Software Foundation project. Jia explains how they solved the hardest problem in distributed computing, spatial partitioning, and why the industry is finally ready to move away from silos and into the spatial lakehouse. We don't just look back, we look forward to why AI desperately needs spatial tools to evolve.
If you throw out this question to AI, it won't be able to understand, right? Because it has no geospatial knowledge. It does not understand the real physical world. In the next couple of years, more and more people are going to be interested to get spatial intelligence, right? So the tools that can help you drive spatial intelligence are going to be the key.
From the architecture of the cloud to the future of AI, the future is spatial. So let's get into it. All right, we'll go into it. So, Jia, I'd welcome. Obviously, we know each other, and good to have you here and get a chance to talk out in Arizona, kind of where everything started. Sounds like, but let's get in. I want to hear, obviously, introduce you to everybody. So, tell us a little bit about you, your background, and kind of how things got started on the journey with Sedona.
Great, thank you, Matt. My name is Jia. I'm a co-founder of Whereabouts. I'm also the co-creator of Apache Sedona. Basically, right now I'm leading the open source community of Sedona as well. So we started the Sedona project a little bit over 10 years ago in 2015. And at that time, the project was called GeoSpark. So, at the time I was doing my PhD at ASU, right, together with Mo Saward. And the point of working on GeoSpark project is that so we want to publish a research paper to design a system that is able to handle big geospatial data using cluster computing engine, right? And so we published a bunch of papers, and then after that we dumped the code on GitHub, right? And then we moved on, right? So we work on other research projects, other research papers, but I was still maintaining Sedona for years, for a couple of years, right? So as a side project. So after a couple of years, around that was started in 2015. In around 2017, so we started to have lots of people to started to participate in the community and started to contribute and also submit patches and also create tickets, create bug reports, right? And after that, we keep adding new features to at the time GeoSpark, right? And in around 2020, so GeoSpark joined the Apache Software Foundation and eventually became a top-level project called Apache Sedona, right? And just like other very famous Apache project like Apache Spark, Apache Hadoop, so on and so forth. And after we have Sedona became a top-level project in Apache, right? So in around 2022, so at the time the downloads of Sedona was about 500,000 per month, and the overall downloads of Sedona at the time is like tens of millions, right? So at the time, I already got my PhD, I already graduated. I was a faculty member as well, so I was a professor of computer science at Washington State University. And Mo still was still at ASU at the time as a professor. So we were talking to each other, and we both were busy, right? We figured that, okay, so maintaining Sedona as a side project no longer works, right? We either go big or we don't do it at all. So then we started to think about, so why not we start a company, try to commercialize Sedona, because we see Sedona already were able to solve lots of pain in the community, right? So that's why in 2022, Mo and I, we started the company Whereabouts, try to build a cloud-native data warehouse for processing geospatial data, right? So that's how we started the company. Now, fast forward to now, 2025. So it has been a couple years since we started the company. So both the company and the open source software is doing great. So on the open source Sedona side, so right now the monthly downloads of Sedona is about like 2 millions per month, which is great. And the overall downloads of Sedona has exceeded about, I would say, 60 millions globally. And also the company is also doing great. We have right now about like 40 people in the company. We have customers from different industrial sectors, right? Yeah, so that's pretty much about the history, how it started.
Great. And what I really find interesting is, so you started with GeoSpark, and I mean, this is all the way back in 2015. So it's really a 10-year journey we're talking about here, with a couple thousand downloads all the way up to 2 million monthly now, and that's a huge span and a huge, journey to go down. On top of that, moving from, building it within academia, getting it sponsored by Apache, going all the way to now building into a full product, and a product that both supports the open source but also has the cloud-backed platform and things like that. I think that's what's really interesting, is there's this really long history that maybe not everyone sees, because you've been working on this for 10 years, and even before that, just maintaining it out of all the work that goes into that, and managing bugs and managing the community and everything like that. I wanted to step all the way back to the beginning to kind of figure out why does geospatial data need to be treated differently, right? There are big data platforms. You mentioned Spark, Hadoop, things like that. What particularly made geospatial data interesting to you when you first set out on this project that required some different treatment than the rest of the data types in the world?
Great question, right? So to me, geospatial data is definitely special from a couple different aspects. So I would say the very first aspect is geospatial data is very complex. If we use the modern words now, the buzzword now, geospatial has the multimodality problem by nature. So when I say multimodality for geospatial, that means, so geospatial data is not just about like points, right? Like longitude and latitude, right? It is about everything. So longitude, latitude, right? Polygon boundaries, trajectories, right? So those are geospatial data. However, there are even more geospatial data that are in very different data type or shapes. For example, satellite images, drone images, right? LiDAR data. So all of these, they are geospatial data, right? They're very different, right? So the satellite data you captured, they are similar to imagery data, right? With geospatial information in that, but it is so hard to process, right? So this kind of multimodality problem make the system really, really hard to process all the data, all the geospatial data in one place. So that is one, so multimodality problem. Secondly, I would say the geospatial queries or geospatial operations are very hard, are very different from traditional or generic data processing, right? So think about what do you do when you have regular data, right? You do like a polynomial, right? A plus b, a plus 1, a minus 1, something like that, right? But what do you do with geospatial data? So you check their spatial relationship, right? If A intersects B. Although this sounds simple in an English world, but like it is actually it involves very complex mathematical or computational geometry operation, right? And there are other operations, for spatial operations. For example, I want to do upsample downsample on satellite images, right? I want to do map algebra on satellite images, right? So all these operations, they are very, very unique to geospatial, and most importantly, they are compute intensive, right? So this is you can do that on your laptop, on your desktop. It is okay, you can do that, but it doesn't work, doesn't scale if you have relatively large data set. Doesn't have to be real large, it just need to be relatively large, right? Then it just does not work, right? So that's the, I would say, the two main reasons that make geospatial data really, really hard to process, and also to make it hard for people to make sense of those data.
Yeah, and correct me if I'm wrong, but I think you came from like a database background, right? That was kind of your core focus. So you're understanding data systems, all these different pieces, and then you're combining that with the geospatial. Why then, and what is the need for the distributed computing there? Because you mentioned, okay, there's certain things you can do on your laptop. There's a certain amount you can achieve. We all know it. We've put things in a desktop and crashed it before. When do you need to go to a distributed computing system, which is sort of the underlying infrastructure of Sedona? And what advantages does that bring to someone who's trying to process like a lot of this data at once?
Great. So to me, I think there are a couple reasons you want to go to distributed compute or go to like cloud native data warehouse or data lakehouse for processing geospatial data. So of course, one is that so the data, when the data is large, right? When you have super large data, say when I say large data set, I mean like a couple hundred gig and 1 terabyte, something like that, and the things go beyond that, right? So when you have this kind of large data set, sure, I would recommend that you use probably distributed compute for that, or cloud native data warehouse for that, which is great. But that's just one aspect. Another aspect is if you have super complex operations, right? Remember I mentioned that, so one of the challenge of geospatial data is the geospatial queries or geospatial operators you want to perform, right? So if you want to have, for example, something like spatial join, right? That's a fundamental building block operator in spatial compute. So even if you just have very small data set, say 1 gig or 2 gig or 10 gig, if you want to perform a spatial join or self-spatial join on this one single data set, if you don't have an efficient or scalable engine, it's just going to take you forever, right? It probably don't crash even. It just keep running, and you're going to spend your whole life on that, right? Yeah, that's my my 2 cents.
Yeah, it's when I talk to a lot of people about scale in geospatial, like in most cases in the non-spatial world, it's like number of rows or maybe number of columns or maybe some complex data types, right? But when you dig into the data type of, let's just say, a vector polygon, some of those can, like some census polygons are 2 megabytes, just that single polygon itself.
Yeah.
And then, the number of vertices that go along with that, combining that with raster data, combining that with, the spatial operations you're doing. Are you expanding the geometry, creating a buffer? Are you clipping it? So it's not just number of rows, but, you have to consider the shape of your data, the shape of the individual polygons you're dealing with, how different are they? And I think that's like, when you talk about big data in geospatial, it's not just the number of rows, right? That it's kind of a trap that I can kind of see people falling into. But what's nice about Sedona is that the distributed system allows you to move that around efficiently and then really understand the spatial relationships of that data, which is, where a lot of the work that's happening at Whereabouts now is going into. But before, obviously, you started Whereabouts, you had plenty of years just maintaining this as an open source project with a massive community. Lots of people requesting things or, asking for changes or finding bugs and deploying it in different systems. Talk to me, and I think that was probably the first time we met was at one of the Apache Con, what it was called back in the day, but code community over code now.
Right.
So I remember chatting there, and it was still pretty crazy to me just how many people were there. I think it was in the middle of COVID actually. There was this massive event of open source enthusiasts from all over the Apache ecosystem. But talk to me about what it takes to truly maintain a thriving and vibrant open source community like you have and continue to do to this day.
Yeah. So to me, I would say to maintain a vibrant or active open source community, the most important thing is for the original creators, right? You need to be really excited about that. If you are not self motivated, right, you will never be able to make it successful. Because when I started GeoSpark or Sedona 10 years ago, and also while I was maintaining Sedona, right, I didn't know I'm gonna start a company. I didn't know that. It's just my hobby. It's just like I I feel so excited to see people use that, right? I want to keep working on that. I want to make sure the thing that I wrote can help people, right? So that's the thing that I think this is the key for the original creator of the project, right? You need to you need to love the project. You need to spend time. You need to work with the community to help people. I think that's the fundamental first thing I would say. However, the second thing to make a open source project really successful is you need to be able to foster a community, to create a very, very active community. Because, when you look at all the current, any large or large scale software right now, no software is actually purely written by a single person, right? You need to have a community. You need to have lots of people to help you test the software, right? To help you contribute to the software, right? So, and although it sounds like, yeah, everybody wants to have a community, right? Everybody knows it is important to have a community, open source community, right? But in fact, it is not easy to actually create a welcoming environment in the community, right? So like, it is not easy to actually encourage people to actually start to contribute to open source project, right? So we spend quite some time on that. Although we are still working on that, right? But I think that's another important thing, and we got some good experience on that, but we are still learning and still working on that. And we actually appreciate that there are lots of people in the Sedona community willing to work with us and contribute to the project.
Yeah. How many issues do you think you've personally handled in the Sedona repo over the years?
Yeah, at least hundreds.
Yeah.
I don't remember that. There are a lot.
Yeah. I mean, that's the remarkable thing is like, I think, every time I go in there, you're responding, you're keeping it updated. I mean, there's a ton of just effort to keep things moving, and you've been doing it from, its infancy all the way up to where it is now. And it's, Sedona, what's always been, I don't want to say surprising, but just, maybe shocking is just how many big organizations, people are using it different ways across, all different countries and everything, which is one of the cool parts, that you can build something that can just go so many places. When you were building this, like at what point did you kind of start to sense like, oh, there's something here, you're seeing traction pick up? Were there specific like features or things that you put in place or that the community suggested that were like really help move things along? Like walk me through that journey of like when you're like, oh wow, this is really starting to grow.
Yeah. So great question. And that's also something that I like to share, and not a lot of people actually realize that, but I have some sort of first-hand knowledge or experience of building these kind of features in an open source project, right? So when we started Sedona 10 years back, so we started that as a pure Java Scala project. And in terms of interface, so we have a bunch of Java Scala function, right? You just do function call, and those function name are random name. I just pick a random name I want, right? Like, okay, do spatial join, right? Something like that. And people, it's okay, like they're okay with that, they use that, right? That's why how we started, right? But like we see traction, but it is not that high initially in the first few years, right? But I would say the features that really make Sedona take off is, I would say, two important features. The first thing is what we call spatial SQL API, and the second thing is what is our Python API, So those are the two things that really makes the product really successful. So in terms of Spatial SQL API, so in around 2017, so people started to ask like Java Scala is so hard to use, right? I just want to do things using SQL. SQL has been out there for decades, right? People just want to use SQL. It's so simple. I just want to use some sort of declarative language to tell the system what I want. I don't want to tell you how to make it work, how to make it run efficiently, right? So I heard it, right? I heard the need from the community. So we started to add spatial SQL function, right? And the SQL language support in Sedona. And after that, we see a big spike in terms of usage, right? Lots of people started to use it, right? And of course, I need to also thank the PostGIS community, right? So when we started to design the Spatial SQL API, so there is no golden standard out there. Of course, there are some industries like OGC simple feature standard out there, right? But what we really learn a lot from is the PostGIS. Is the post in terms of not only the function but also the behavior, right? We try to maintain the same behavior of the PostGIS function. And after that, in about 2019, we also noticed one thing in the data science community is that Python really started to pick up, right? Lots of people, because of AI, because of data frame API, right? There are lots of things at the time going on in the data science community for Python, right? So people started to rethink the design for all programming language, all software in terms of Python interface. So we introduced Python interface in 2019, right? And then there's another big spec on top of that, right? So fast forward to today, right now I would say 80% or 70 to 80% of our users, they're actually using a mix of Python plus SQL, spatial SQL in Sedona, right? Only about 10 to 20% people, they are using the remaining sort of APIs, Java Scala. We also have R bindings as well. So people are also using R on top of Sedona. But most of people use Python, SQL, or a combination of both.
Yeah. I mean, when I first kind of came across Sedona and I saw it was Scala and Java, I was like, that's above my skill set, But then I was, as I was watching things, once you add SQL and then once you add Python, that's when things they become a lot more accessible, right? And then, the other part is the back end, which we'll talk about in a minute, like the underlying, the compute, all those different pieces. But just the ability to I used PostGIS for many years, and you can write a lot of, the same exact functions in a very similar way. And that makes things a lot easier. Of course, with Python, it almost, it's a little different, because it's using some, kind of conventions from Spark and things like that, but it's data frame at the end of the day. You can do a lot of those things. And then, of course, the last piece is how you move this down into the compute layer underneath, right? Which is, for a lot of users, Spark underneath Sedona. So I wanted to talk about that, which is, once just the programming interface is one piece, and that helps people use it. It's interoperable with their workflows. It's things they understand and can use. But going down to that distributed compute layer, that's where things really start to take off and go fast. So I want to talk about, just kind of break down, okay, what does that look like, for people who maybe haven't used Spark or haven't used a distributed computing system, like what's happening under the hood there? How is the data getting moved around and what's taking place? And then more importantly, what are the considerations you need for something like that with spatial data?
Cool. Great question. So I think for a distributed system to work, or distributed compute system to work, or cluster computing engine to work, I would say there are a couple fundamental things, right? So for example, one of the most fundamental thing is how would you coordinate schedule jobs to all machines in the cluster, right? You have, say, hundreds or thousands of machines in a computer cluster, right? So how would you schedule a task among different machines and make sure everybody is working, right? So gladly, so when we designed Sedona, right, we were able to leverage the computing framework from Spark, and we also use Flink, also use Snowflake to handle those issues, right? So it is working fine. But on the other hand, another big problem for a distributed compute or cluster computing engine is that how would you divide the work? How would you so think about you have big project, right? Now you have 10 workers, right? 10 machines or 10 workers to help you. So how would you divide your job to 10 pieces such that each worker get a fair amount of work to do, right? Nobody is overstressed, but nobody is stay idle, right? So that's another fundamental piece, right? So for generic data processing, right? So there are different ways to divide the work. So we in the database community, we call it data partitioning or distributed data partitioning, right? So there are different methods to partition data, like hash partitioning, like round robin, so on and so forth. Very different methods. They all have different pros and cons, right? So when it comes to geospatial data, this is also a fundamental issue. However, when it comes to geospatial data, this is much, much harder, right? So this is simply because there are two things you want to consider when you do data partitioning for geospatial data. So, like I said, the fundamental goal is you want to make sure everybody get a fair share of the work, right? But when it comes to geospatial data, you also want to make sure that you want to sort of preserve spatial proximity for the data when you do the partitioning, right? So later on, when you have a query or operation that asks for a specific region, geographic region of data, right? You don't have to actually ask so many machines. You don't have to say you have 1,000 machines in the cluster. You don't have to check every single machine in the cluster to get things done, right? So that's why you want to sort of preserve the spatial proximity so that when this kind of query comes in, you only send it to a specific geographic region, which is on a single machine, right? This sounds simple, right? But it is fundamentally hard for geospatial data because the geospatial data, it is not just a point, right? Long-term latitude. It has a multimodality issue, right? You have raster data, you have polygons, right? You have LiDAR data, right? So how would you count the size of the work when you have different type of data, different type of geospatial data, right? And how would you separate geospatial data if you have very weird spatial, actually not, I would say weird, right? There are lots of geospatial data. You think about the boundary of the United States, right? And compare that with the boundary of another country in the world, right? So say South Korea, right? So they are both at country level, but of course USA boundary is much larger than the South Korea one, right? Now you sort of need to put both in the same data set. You need to have some sort of query to query both of them. It is extremely hard to actually partition them into the same geographic region, different machines, right, based on their geographic location. So that's the second fundamental thing. I would say that's the core of a geospatial aware cluster computing engine, distributed computing engine.
Yeah, I mean it's. I remember looking at there's some different blogs you put out and articles and of course papers and just to call this out, I know you guys recently got a really big award for this the 10-year kind of history of Sedona and everything like that. So congrats on that, first of all. And what I realized looking at all those different pieces is when you're partitioning if it's just regular data, maybe if you have like a date and some text and maybe some numbers, you can split those things out. It's not too difficult. Maybe you split by dates or groups like that. Of course, the data might be uneven and there's some considerations there. But spatial data, forgetting multimodality for a minute, just the distribution of like just places, points of interest. Or, there's clusters in cities, there might be outliers, there's, things in different areas. You don't want, one worker calling something on a different machine that's all the way across the country, or all these different considerations that make it just difficult. It's a tough problem to solve, right? So just moving that data around or putting in the right place, there's a lot of things you have to consider there, which was just like, once I started to click, I was like, oh, now I can see how this works. So I wanted to talk like, okay, you've taken Sedona very far. It's now 2022, and you're deciding we need to turn this into a platform. Why do you need to turn into a platform, right? Why does it need to have a cloud behind it? And what does that allow you to do all of this stuff even more efficiently than you could just on your own?
Great question. So, couple things, right? So, first of all, there are two things here. Two things we're building in Variables, or two core we're building at Variables. So first of all, it is cloud or cloud native, right? Secondly, it is data lakehouse or data warehouse tailored for geospatial data, or treat geospatial data as the first-class citizen, right? So first of all, in terms of cloud, right? So we all believe in cloud, and I believe cloud is the future, right? So I don't have to repeat all the benefits of cloud, right? Easy to use and auto scaling, all this kind of stuff, right? So we believe in cloud, so we believe everything should move to the cloud, right? So that's why we went all in on cloud native data lakehouse. But on the other hand, so we also see that right now, all the existing general purpose data lakehouse, data warehouse engine on the cloud, so they all have some sort of geospatial functionality. So they are great, and they are great at scaling, right? However, their spatial functionalities is just basic functions, right? So they don't allow user, they're not able to enable user to perform any complex geospatial operations, right? So that's why we also feel that we should build a platform that have all the geospatial functionalities baked in, so our customers can just log into a platform, of course with the ease of use, all the benefits of cloud, but on the other hand, also has advanced capability to process geospatial data, in particular to make sense of geospatial data, right? So that's why I think why we decided we start a platform, our SaaS business, to actually like this, right?
Yeah, I think when I look at what Whereabouts has put together, right? There's obviously you have a lot of control in the compute, right? There's and to get into the weeds, there's like understanding how spatial predicates go down, and you can distribute data. How the spatial joins just go blazingly fast. You have complex things like KNN joins, and then obviously like the raster vector interoperability. All these things go just quickly because the cloud system that you built understands spatial data, right? That's to oversimplify it, right? All of the compute understands what's happening with spatial data and knows where to send it, and all the stuff we just talked about can happen really efficiently. But then there's a second piece that was the lakehouse, right? And I've talked about data lakes. Lakehouse adds kind of the the management or architecture. Obviously, you've also made a big push on Apache Iceberg and getting geometry types adopted there. And I think V3 has been out for a couple months now, which has the geometry type, and we're seeing other platforms upstream start to adopt that. Which is, I think, what's really cool is if you have an Iceberg table that has a geometry, you now have basically zero ETL into these other systems, which is going to be a really good vision for the future. There's no data transfer. I just point my other system at the tables and it works, right? Which is really interesting. But I want to talk about, kind of why, what's your vision for the spatial data lakehouse? And why is it taking so long for the Lakehouse to get, or like Geospatial to get into the Lakehouse, right? Lakehouses have been around for, several years now. They've, worked across many different systems, different, people push those forward. But why is like Spatial just now in 2025 showing up in, the Lakehouse?
Yep. I think there are couple of reasons, right? So first, let's take a step back and look at what's the definition of a lake house, right? So I would say there are two fundamental things in a lake house architecture. So first of all, you have compute and storage decoupled architecture. So that's one. Secondly, another requirement for a lakehouse architecture is the data has to be stored in an open data lake format, right? So there are a couple of open data lake format out there, such as Apache Iceberg, Delta Lake, and also Hoodie. There are a couple more out there, right? So for the compute and the storage decoupled architecture, it is people understood that, and I don't think it is a blocker, or it is actually hard for people to actually adopt geospatial data there. But what was really hard for people to actually use geospatial data in lakehouse architecture is the open data lake format. That is the part that is really, really hard. So first of all, there are a couple of reasons behind that, right? So first of all, in the past few decades, geospatial data is great, but everybody say geospatial data is special. Of course, I agree, it is special. That's why we need a special tool for that, right? But geospatial data shouldn't stay in data silos, right? They shouldn't stay in a number of weird proprietary formats, right? And here and there, right? And if you are working in the geospatial area, you know what I'm talking about, right? Think about the GDAL, right? Think about how many data drivers it has, like hundreds, right? It's just to read all sorts of weird formats, right? So these things make it really hard to actually have all the data stored in a single place. It is really, really hard because like you need a driver, hundreds of drivers to understand data formats, right? And on the other hand, another big part is that, so when you say open data lake format, right? So what does open mean here? So the open here, there are a couple of things. First of all, definitely it is open source, right? However, another thing is it needs to be under open governance, so that, because think about that. So when you store things in an open data lake format, right? You'll be able to use multiple engines, different engines, to read and write the same table and to operate on same piece of data, right? So that means all these engines, the BigQueries, Databricks, Variables, Sedona, right? Also, these engines, they need to agree upon the same standard, right? They need to all be able to operate on the same standard, such that you don't have to copy data again and again. So that's why actually people need to reach consensus on the data format, right? And when it comes to geospatial data, it is about how you store geospatial data in the open data lake format. And there must be a standard. There must be a protocol that everybody agrees upon, right? So it actually took us lots of time to actually bring geospatial data into an open data lake format. So you mentioned Iceberg, right? So earlier this year, so we managed to push geospatial support into Iceberg v3 spec, and after that, other popular open data lake format also followed up, including Delta Lake, including Duck Lake, right? So they all follow the almost identical spec we have for geospatial data in Iceberg. They just take that and put it there. So looks great, right? But do you know how much time it took us to actually bring it in? Couple years, just couple years. Although when you look at the spec, it's just like WKB, it's just like geometry data type, CRS, this thing that we already know, right? But surprisingly, it took us a couple years to get there. So first of all, we have a prototype, right? And then we have a production level data lakehouse we call Havasu, which is an extension on top of Iceberg. We have that in production in Variables a couple years back. And after that, we started to talk to the community. So why not we bring in this into Iceberg natively instead of have a extension only in variables? And there are around 10 different companies come in, and we have lots of meetings, spend lots of time to discuss. So what should go in, what shouldn't be included, right? We spend lots of time on that. Couple years again, and finally in 2025 we are able to make it to get into the Iceberg format. So as you see here, so it is a discussion and the collaboration agreement, right, among all parties that actually take time. And because Geospatial is hard, it's not easy to understand, we need to actually sort of teach all the different parties, different companies to understand the characteristics of Geospatial data. Then we can have they all agree upon the protocol.
Yeah, there's when you realize how much discussion and time and thought went into all the work to get it there, like it really starts to like it's pretty crazy. And there's all these other parallel efforts, of course, you know, with Parquet and GeoParquet adding that spec and support, even things like Arrow and all. There's lots of other kind of peripheral efforts that are helping grow things and stuff like that. And then you mentioned other engines, right? The fact that one table format can read into multiple different places, be it Sedona, be it Wherebots, be it, you know, upstream data warehouses, you know, all these different places, is that alone is just a pretty remarkable thing. And I think that's the vision that like really kind of blew my mind, is to, you know, to say, you know, I have this remote data that's sitting on some bucket somewhere. It's tables, it's governed, it's structured. You know, it's not just a bunch of files that if I overwrite them, I lose all the history of it. But now I can connect that into any other system I want to. And speaking of engines, you know, Sedona recently did something different, right? Built a new engine, right? And I think, you know, I wanted to call that out here as well, which is SedonaDB, which is, you know, a single node engine built on Rust, using Apache Data Fusion. Like, why do we need another engine, right? You know, you have this engine that you put 15 years of work, or, you know, 10 years of work into from 2015. But why do you need this other engine, and what does it enable now? You know, both individually and then in unison with something like Sedona and Wherebots.
Cool. So we released this single node engine called SedonaDB a couple months back, right? So the reason why we even started this project is that we realized there is a fundamental blocker in Apache Sedona before, that is ease of use or installation, right? So whenever you want to do something in Sedona, right? So the very first thing you're gonna do is that you're gonna have to start a cluster, compute cluster, right? Cluster means like machines, number of machines, right? Yep. Like it is not easy, right? Especially when people just want to process a relatively small amount of data, right? It's just not that easy. Of course, we have variables, right? Of course, we have cloud, right? So all those things make those kind of development or installation much, much easier. That's why cloud is great, right? But on the other hand, so in some cases, you just want something that is very easy to use, and you can quickly install that on your laptop, and you just work on that, right? So we noticed this is the problem with the Sedona ecosystem, with the Sedona users, right? So we were thinking about, so how can we fix that, right? How can we fix that? So that's what actually motivated us to actually develop SedonaDB as a single node engine, right? But on the other hand, so SedonaDB is not just like a simple copycat of other existing, single node geospatial data processing tools, right? Like GeoPandas, right? Of course, the API we try to keep the same API, right? However, we have lots of innovation in SedonaDB based on the experience we have in maintaining Apache Sedona, right? So a couple of things that I actually didn't mention before regarding the design of Sedona. So we talked about distributed task scheduling. We talked about distributed partitioning, right? But there's another fundamental thing in a distributed database or distributed computing engine, that is query optimization of spatial query optimization, right? So we did lots of research, both from academia, also from our industrial experience maintaining Sedona, right? We have lots of experience that, and we actually took that part as well and put that into SedonaDB. So when I say spatial query optimization, that is, if you have spatial query, right, the database engine going to be automatically determine what's the best query plan to actually execute the query. Even given the same SQL query, so every time it might actually follow different pattern, different algorithm based on the input data, based on the characteristics of the input data set. So we have all that into SedonaDB. The only thing that is missing is the cluster or distributed compute part, which is on purpose, right? But we keep all other good things into SedonaDB, such that when we released SedonaDB a couple months back, we did a comprehensive performance benchmark, right? So SedonaDB outperformed a couple existing tools, right? Because of the research and the innovation we did in SedonaDB.
Yeah, I think it gives people a really accessible entry point, to start testing, and it's fast. I mean, forgetting that it's easy, but it's also incredibly fast and it can move quickly. Obviously, we've put out spatial events that allows anyone to test and compare these systems on a level playing field, which really didn't exist before on top of that. So not just the testing, but the easy install, the ability to read in, and I think just an easy way to get started and get up to a certain level without, kind of the task of standing up your own system on the back end. So I think, you've seen this all and you've been involved in this for the past 10 years, right? Given all the things you see taking place right now, I mean, I think we've mentioned like 6 or 7 Apache projects, different technologies, cloud technologies, all the stuff that's happening right now. What do you kind of see as the vision for the next, 3 to 5 years? Like, what is everything going to keep? What's the direction things are going to go in? What do you expect to take place? What should people be watching out for? And if they want to get involved, how can they get involved as well?
Great. To me, I think I'm gonna limit the scope into like geospatial, the geospatial world, right? So I think a couple of things gonna happen for the geospatial industry in the next couple of years, and actually some of them are already happening, right? So first of all, there are gonna be no geospatial data silos. So geospatial data gonna go all in to the open formats, to some sort of unified formats, right? Or open format at least, so that people will be able to use different tools, but only a single copy of the geospatial data. So that is already happening, right? So that's going to be the future. And I would say another thing that is that's going to happen is what we call people want to have more spatial intelligence on the real physical world. That's gonna happen really, really soon, right? There are lots of things going on in the AI world, right? So like there are lots of people talking about world models, right? They are seeing the current AI models or LLM models, right? So they don't understand the real physical world really, really well, right? They don't understand the physics, right? So that's actually the reason why you're gonna need spatial intelligence, and that's why actually more and more people are gonna need spatial intelligence to understand the real physical world, right? So think about the AI or any tools you have right now. So they still cannot easily understand some very fundamental or very simple geospatial queries to understand data, right? For example, if you ask the AI tools or any tools you have, so what is the nearest restaurant close to a certain location, right? And what is the nearest restaurant close to a number of locations, right? It is a very simple function. If you throw out this question to AI, it won't be able to understand, right? Because it has no geospatial knowledge. it does not understand the real physical world, right? I think in the next couple of years, more and more people are going to be interested to get spatial intelligence, right? So the tools that can help you drive spatial intelligence going to be the key to the in this journey, right? So that includes data processing tools, that including the AI tools as well. So all things combined should be helping people to achieve the spatial intelligence.
So last question, if people are looking to get started, right? If they're maybe coming from different systems or in different tools or just getting kind of started on this journey, what do you suggest for them? Because there's a lot of momentum, there's a lot of change. How can someone kind of jump in and get started by in this new ecosystem that's being created?
Great. So of course, now you have all sorts of different AI tools, right? You can do web coding really quickly, right? So I would say, try to start with some sort of basic AI tools to do some sort of web coding with the geospatial tools you have, right? So you can do that on top of SedonaDB variables, but not only that, right? So there are traditional tools you can also use, traditional geospatial tools you can use, right? So do some web coding around that to better understand how things going, right? And after that, right? Just don't those tools, those AI tools are easy and they're really good at helping you get started, right? But after that, try to learn a little bit more about those tools, right? How these tools work internally, right? If you want to really dive deep on understand how, in particular, for geospatial data, right? In particular, if you want to understand how geospatial data works and what geospatial data is, right? So like I said, there are lots of challenges, complexity when it comes to geospatial data tools, right? So and like I said before, many of the AI tools, they still don't understand geospatial, right? So after you get started, be sure to actually get your hands dirty and try to understand what's going on with those operations, spatial operations, what's going on with those kind of spatial AI models, right? So then I think you'll be good to go.
Yeah, I like that you called that out because number one is just learning the operation of it. The languages, be it SQL, be it Python, being able to do the different operations is one step. And like you mentioned, you can get pretty far with a lot of the tools that exist, be it AI, enabled coding or just kind of learning and going through tutorials and stuff like that. And there's lots of great tutorials, obviously, on SedonaDB is like a very easy place to get started, right? There's Python, there's code, there's open data in open formats that you can just kind of go out and use. But I think, calling out the architectural thinking, kind of understanding when you run ST intersects, what's happening under the hood? How's that data getting moved around? And how is it interacting with the different data sets? Is that different if it's a point, it's a polygon? Once you understand those pieces, and that's really it's not to say that you need to learn how to set all that up, right? There's different platforms that solve that for you. Whereabouts solves that for you, right? You don't need to understand and actually do that. But understanding how that works and how that sets up for the functions you're writing and all the different stuff can really help you understand what's happening with these systems. And it, again, helps you understand all of the complexity that's taking place under the hood, all the complexity of the 10 years of effort you've already put into this. And I think that's a really important point to call out, because once you kind of start to understand that, you can really, unlock a lot for what you want to do and go from there. Well, this has been great. Thank you for taking the time to sit with me. Depending on if you're watching this, it'll be in the video description, or if you are listening to this, it'll be in the show notes. We'll include a bunch of links, obviously, to SedonaDB. I'll include some of the talks and papers you've done. Anything else you kind of wanted to leave everyone with today?
So I would give a shout out to the Sedona community, right? I want to thank all the users and contributors of Sedona, right, that help us go this far. And on the other hand, I would also encourage all the folks who are listening to this podcast, right? Try to start to use geospatial tools. Try to use SedonaDB, Variable Sedona. All great, but not limited by those tools, right? Use any tools you have. Try to start to learn geospatial data. Try to learn how the real physical world works, right? Do it today.
Yeah, that's good. Well, Jia, thank you. It's been a pleasure. And yeah, we'll be talking again soon.
Yeah, thank you.